Okay, welcome back everyone to our first Kadnov seminar, maybe Lineweber seminar. We're still unsure about the name of the new year. We're very happy to have Adar Sharon visiting us from UCLA /
I think it's officially Simons for 2 weeks.
For 2 weeks, okay. He's currently a vagabond, transitioning from place to place, and he's going to tell us about bootstrapping CFTs with moduli spaces.
Yeah, thanks for having me. Right, so I'm going to talk about CFTs with moduli spaces. So I'm going to start by talking about what a moduli space is. So let's imagine some just classical field theory with two fields, scalar fields, phi1 and phi2, and I write a simple potential. It's phi1 squared, phi2 squared. I'm going to analyze the space of vacua of this theory. So this is always positive, so the vacua are wherever the potential just vanishes, which is if phi1 vanishes and phi2 is arbitrary, or phi1 is arbitrary and phi2 vanishes. So this simple theory, at least classically, has a continuum of vacua, not just one point on the discrete point, but a continuum of vacua, and I'm going to call this continuum of vacua a moduli space. So these things are very easy to cook up classically, but quantum mechanically, there are corrections to this which generically will lift this moduli space. So even in this simple example, once I include quantum corrections, the symmetries of the problem don't prohibit something like a mass term showing up. And this mass term immediately lifts all of these solutions, and the only vacuum is at the origin, where both of these vanish. So quantum mechanically, there's no moduli space here. There do exist theories with exact moduli spaces, but for that, we're going to need some additional symmetry that prevents these terms. And the only way we know how to do that so far is using supersymmetry. So supersymmetry protects these moduli spaces. And it makes sure that in some cases, there's no corrections that live. So let me give actual examples of moduli spaces that are there even quantum mechanically to all orders. So I'm going to give two examples. One is a very supersymmetric example. One is a not very supersymmetric example. And most of my talk will be around these types of theories and not around these types of theories, or similar to these. So very supersymmetric is 4D and equals 4 within mils. This has some gauge group that we're going to choose to be SUN. And in particular, it has a bunch of scalars, xi. These are scalars I is 1 to 6. And they are in the adjoint the gauge group. And there's a potential trace of the commutator of xi. So we can start with just treating this potential classically, and you can easily see that there's a moduli space where I choose all of these fields to be diagonal. So x1 is something like a1 to an, and everything else vanishes. x2 is b1 to bn, and so on. Then these things commute, and the potential vanishes, so we have a moduli space. So this thing has a huge moduli space classically, which is of the order of 6n dimensional. And because it's very supersymmetric, supersymmetry protects this potential, and there's no additional terms that come up from quantum corrections. And so this huge moduli space is just exact quantum mechanics. So there's a huge, huge moduli space here. A simpler example is 3D n equals 2, and it's called the XYZ model. So 3D n equals 2, if you're not familiar with it, it's very similar to 4D n equals 1. So if you're more familiar with this, and it's nice. What we do is we take three chiral superfields, x, y, and z, and we write down a simple superpotential, which is a problem of x, y, and z. Classically, to find the moduli space, what you do here is you solve something called the F-term equations. The F-term equations give you the moduli space, and these are you take a derivative, a w with respect to each one of the fields. And you set that to 0. So phi here is x, y, and z. So these are really simple equations. xy is 0, yz is 0, and xz is 0. And the solution is that either x or y or z can be non-zero and arbitrary, with the other ones all vanishing. For example, we have one grand, which is this, and permutations. Again, this was all classical, but supersymmetry is magic, and it protects this moduli space to all of the perturbation theory, and quantum corrections don't lift this moduli space. Okay, good. So let me talk about what I want to do today, why and how. So the descriptions I've given you so far of moduli spaces all use Lagrangian. So in every example, I took a Lagrangian, I had some potential, and then I used that to find what the moduli space is. But we know that QFTs and CFTs in particular, we understand them on a more abstract level now. So we know CFTs are defined by some set of dimensions and OPE, and something we call CFT data. And the basic question I want to understand is, how do I know just based on CFT data if there's a moduli space or not? So there's two directions to this question. So given CFT data, some dimensions and spins, OPE coefficients, is there a moduli space? And then there's the opposite question. So given a CFT with a moduli space, what is the constraint on CFT data? What constraints? Okay, so let me talk about why we're doing this.
So in general, can this kind of question be addressed by quantizing the Goldstone boson theory?
That's part of what we're going to do. I'm going to do the effective action. In general, I don't know how to do that without some additional assumptions. So what I'm going to be doing is assuming it's not just the dilaton, which is the main Goldstone boson that's going to show up, but also assuming some other U1 symmetry. And with that additional U1 symmetry and its Goldstone boson, I can get some information. But in general, I'm not sure how to understand the CFT from this effective field theory on the moduli space.
Okay.
So yeah.
Sorry. Sorry. Hi. Are you excluding superconformal moduli, or you're including like the tau parameter of n equal 4 in the story?
Not the tau parameter.
Yeah. So
what I gave here.
yeah. So it's not preserving conformal invariance necessarily.
Again, sorry. Oh, sorry.
Like
not conformal manifolds. Yes, not
conformal manifolds.
That's
okay.
right. I know. I get this question every time, and I forget to cite this. Yes. So for example, in n equals 4, we have another thing that sometimes is called the moduli space, which is the gauge coupling. That parameterizes a space of CFTs. That's not what I'm looking at. I'm looking at giving vacuum expectation values to these fields S.
Good. Thank you.
Okay, so why? So first of all, this is a fundamental question, and I was honestly surprised that this hasn't been answered before. So when we just started this project, I assumed this was somewhere in the literature, because this is just a very basic question that for some reason we haven't found the answer to. Another reason to look at this is that there's this program of classifying supersymmetric CFTs with enough supersymmetry. In particular, there's these 4D n equals 2 CFTs that people are trying to classify. And part of the way people classify this is using the moduli space. So assuming a moduli space of such and such dimensions, they can basically tell you what type of CFT you're looking at. And understanding this type of question better will also play into this program of classifying the supersymmetric CFTs if we understand how the existence of such moduli spaces constrain the CFT data. One reason I was excited about this is that this has applications that we'll see to the large charge expansion. And I'm going to talk about this later on. And finally, there's some relation to holography, and specifically this program of the holographic swampland that I may mention at the end. Where basically people started realizing that all examples that we are aware of holographic theories have a moduli space, and trying to ask if there's some fundamental reason that this is true. Okay, good. So how? So like I said, this is some fundamental question. The reason there's no answer isn't because people didn't think of this question, it's because it really is a hard question. So I'm going to start by not solving the question in full generality, but assuming something that makes it easier. So we're going to assume that on the moduli space, there's some additional U1 symmetry that is spontaneously broken. With this extra assumption, we're going to find some universal rule for what it means for a moduli space to exist in a CFT, some formula that tells you at least a necessary condition for this to happen.
Can you explain why that assumption is helpful?
I'm going to be using methods from this large charge expansion. So I don't have a good answer for why without this, I can't just write down some simple rules on the CFT data. We can do something in the full generic case. I'm going to talk about the complete generic case, but there's some, you can call it a bootstrap equation, an analytic equation, but it's very hard to get any meat out of that. So it exists, it's correct, but it's very hard to get information out of that. Here, I'm just going to find some very simple universal formula that's easy to check if it's true or not, or at least if you have the entire spectrum, it's easy to check.
Is assumption 1 always satisfied in known examples?
No. So if you have enough supersymmetry, yes. And with at least 4 supercharges, which is the generic case, yes. And I'm going to mention this in a sec. We have examples where this is not true. And those are the main examples I'm going to talk about today. The examples where this is not true, or the basic framework of examples where this is not true. So let me start by saying what we do know about CFT data when there's a modular space, at least with enough supersymmetry. What is already known? So let's assume at least 4 supercharges. So number of supercharges, at least 4. So this is at least 4d n = 1 or 3d n = 2. Now there's a conjecture, which has been proven for Lagrangian theories, that the moduli space is isomorphic to something called the chiral ring theory. And I'm not going to go into what a chiral ring is, but basically what this is telling us is that directions in the moduli space are only parameterized by BPS operators or protected operators. So,
but that should mean that the chiral ring are functions on, or holomorphic functions on the module.
Yeah. The directions in moduli space corresponds to operators as to BPS operators phi, such that phi to the n is also BPS for any n. And these are the only operators that can get best.
I've never maybe not the right time to talk about this, but I've never exactly understood the fine print of this statement. Like, is that endowing the moduli space with more than the structure of a complex manifold? Is it making it into a scheme? Like, what if you have a nilpotent operator?
Right, yes. So the conjecture is that it is also true for discrete vacua. So all of this is not just the moduli space, all of the vacua should correspond to something in the chiral ring. So for a nilpotent operator, you'd expect n vacua in some sense. This is a conjecture. This has not been proven in general, but yeah, like.
But in Lagrangian theories, that nilpotent part also works?
I am not sure.
Like having a field phi such that phi to the n is an independent operator, this I understand gives you a complex.
I can tell you there's no known counterexample. I cannot tell you the nilpotent part has also been proven. I just don't know the answer. But there's no known counterexample to this thing. But yeah, but in our case, we're going to be interested in this continuum case and not this discrete case. Okay, so assuming this conjecture is true, what do we immediately learn? So first of all of these BPS operators are always charged under something called the R symmetry. There's always a U1 R symmetry in these examples. And so anywhere on the module space immediately breaks this U1 R symmetry. U1 R is always spontaneously broken. So we're always in this condition 1 up there, and so that looks like a good condition to start working in. More importantly, this gives us some constraint on CFT data immediately. So this tells us, maybe I should write this bigger. So an immediate result is if you have a CFT moduli space with a spontaneously broken U1R symmetry, then you have a tower of operators, whatever that means, tower operators with dimension that defined Bn is n times the dimension of phi. So all I'm saying here is that all of these operators are VPS, their dimension is protected, and that's the dimension of phi to the n is just linear in whatever the dimension of phi is. So this is going to be maybe our starting point. So let's call this our hypothesis. With enough supersymmetry, immediately if you have a spontaneously broken U1R symmetry, this is true. And now let's try to guess that even if it's not an R symmetry, if you have any U1 symmetry that's spontaneously broken on the moduli space, then we have this type of behavior. The basic intuition is that far enough away on the moduli space, we should get free fields, and this is basically how a free field looks. So this is something that we might expect at least far enough away on the moduli space. Okay, and indeed, I mean, this specific behavior is true in all of the examples I gave before, in all of the Lagrangian theories. So now let's check this more critically. So what I said was that if you have a U1R symmetry, then this is correct. So what we really need now is an example without a U1R symmetry, some other U1 symmetry, and then check whether this is true or not. And that will tell us if we're close. So we need examples of moduli spaces without an R symmetry. So these are non-generic. They're actually pretty hard to conjure, but it turns out that for 3D n=1 supersymmetric theories, these exist. I'm going to spend a little time explaining what these are and how they show up. Most of what I'm going to talk about for 3D n=1 is a review of this nice paper. Komorgolsky, Wu, great. Okay. Let me review 3D n=1 supersymmetry. 3D n=1 has not been studied a lot in the literature, and most of the reason is that even though it's supersymmetric, the amount of supersymmetry is so small that it's very weak. So usually we use supersymmetry as toy models, where we can actually compute something. In this theory, it's very hard to compute anything, even though you've added supersymmetry, and so there's no reason to add supersymmetry in general. So this has two supercharges. The number of supercharges is 2, which is very small. And as a result, there's no BPS conditions. There are no non-renormalization theorems.
Except for currents.
Sorry?
Except for currents.
Yeah, sure. There's the usual. Sorry, what do you mean except for currents? There's the usual
Currents are in the short multiple of the supercontrol L.
Sure, yes. I mean, let me say there's no protected dimensions, except for the occurrence, whatever it's, yes. So all the usual power of supersymmetry is gone, and there's also no U1R symmetry. But it turns out that even this a small amount of supersymmetry is enough to protect moduli spaces, still enough for moduli spaces. So this has been known for a while, way before this paper, but this paper gave a nice review of how this happens. So let me explain how that happens. So let me write down some simple 3D n=1 Lagrangian. A simple multiplet is a real multiplet, which consists of a real scalar and a Majorana fermion. And the Lagrangian in superspace will look something like this. We have a scalar potential, and we have a pseudo potential. So some things to notice. First of all,
superpotential should be integral over 1 theta.
no. So there's no real difference between the superpotential and scalar potential because it's not enough supersymmetry to do this. So I can't really integrate over 1 theta because then that would be some Grassmannian thing. So this is just like a non-supersymmetric theory where the only difference between a kinetic term and a potential term is that this has derivatives. So the only difference is that here there's going to be some supersymmetric derivatives. There's also no holomorphicity or anything, again, because this is integrating over all of superspace. So there's no U1R symmetry, no non-minimalization theorems, all of the usual holomorphicity things just go away. Also, this is just a real multiplet. There's no reason for this to be holomorphic. So just looking at this, it looks like it's completely useless and supersymmetry won't help. Let me give some simple specific examples. So a free scalar will have scalar potential by d squared phi, where this is some supersymmetric derivative. And it can have a mass term, let's say, which is phi squared. So this will give you a free massive scalar. The potential, if you have this super potential, the potential is still given by this plus some fermionic terms. So how do we still get mileage out of supersymmetry here? So even though there's no continuous R symmetry, turns out there's still a discrete version of an R symmetry. Or sometimes there is a discrete R symmetry. The way we usually find an R symmetry, at least from a Lagrangian description, is that it acts on superspace coordinates. So for 3d n equals 2 or 4d n equals 1, the U1R symmetry rotates this and it rotates this to counteract that. So for discrete symmetry, for an R symmetry, what we need is for this d2 theta to go to minus d2 theta. This is some discrete Z2 symmetry. D2 R symmetry. For this to be a symmetry, we need a super potential to be odd. So crucially, the super potential has to be odd, and this is where most of our results are going to come from. So the fact that it has to be odd is going to prevent certain terms from showing up in the effective action. So let's do a very specific example where we see how this Z2 symmetry is enough to protect the moduli space. This is called the ABC model. So it's still 3d n equals 1. I take three fields A, B, and C, and I write a superpotential, which is A times B times C. So this is similar to this XYZ model we wrote before. The only difference is that these are real superfields instead of complex ones. If these were complex, I would just have the same as 3d n equals 2, and then all of the power of 3d n equals 2 supersymmetry would save me here. The moduli space would exist. So let's do this model. Let's start with the classical analysis. Let's just see if there's a moduli space. We still, just as 3d n equals 2, we just solve the F-term equations to find the moduli space. We find whether dw d phi is 0. And the equations give you that A, B equals C, C, all of these have to vanish. And so we have three branches where either A is non-zero with the other two vanishing, or B is non-zero, or C is non-zero. So there's this weird structure where we have three branches with a moduli space where one of the three fields is non-zero. Now let's do quantum correctness. Let's think of what type of term can show up in the quantum effective action for this theory. So in principle, it's going to be some polynomial P in the fields A, B, and C. Of course, this polynomial has to preserve the symmetries we started off with. And one symmetry we started off with is a Z2R symmetry, where we take, so this is Z2R symmetry, where we take D2 theta to minus D2 theta, and we take A to minus A. Right, so if we look here, then this gets a minus sign, and this dual potential I wrote down also gets a minus sign, so this is preserved. For the effective action to preserve this polynomial has to be odd under A. So the only possible term is something like A times some other polynomial, it's called F, in A squared BNC. But of course, there's no reason to specifically choose A to get a minus sign. I could have chosen instead, B to be odd under my Z2 symmetry. And for this symmetry to be preserved, I also need P to be odd under B. So I would have to have a B outside here, and that would be a function of B squared. And of course, the same thing with C. It's also a valid choice. So the most general form for a quantum correction is ABC times some even function of ABC. And now you can just write down the F-term equations for this most general correction. And you can see that this moduli space is protected and is also a solution to these F-term equations for any choice of this function F. Basically, if two of these vanishes, then it doesn't matter what you do to the third one. So just the Z2R symmetry was enough to make sure that this entire moduli space that might get through here is just preserved to all orders in perturbative. So this is an example of a moduli space with no U1 symmetry, no R symmetry, but not even any continuous symmetry. The only symmetry we really need is this C2R symmetry.
So unlike the cases with more supersymmetry, the R symmetry doesn't have a current here, so it's not part of the stress tensor multiple.
Right.
So is it an option whether a 3D n equals 1 SCFT
Yes.
has a C2R symmetry?
Yes, they don't have to have them. There's plenty of examples with no R symmetry. Yeah. Okay, so now we need to be more careful about what exactly our hypothesis was. So with an R symmetry, we were very confident, and we said, okay, if we have a moduli space, then we have something called a tower of operators with this linear dimension. But now we have examples with no R symmetries, and we don't even expect protected operators. So this exact behavior is very strange. Even before talking about the exact behavior, we need to understand what a tower of operators means. So with an R symmetry, there's no singularities when I take two BPS operators close together. So it makes sense to write down something like phi squared. But with general operators, this is not true. I don't know what phi squared means. So I want to change this a bit and write something that's more well defined for our hypothesis. So let's define a new observable. So given some U1 symmetry, I'm going to define delta min of Q, which is the minimal dimension of all operators of charge Q. So very schematically, here's my entire CFT spectrum. Here's the dimension as a function of charge under some U1 symmetry. This is the identity operator here, and then I have some other neutral operators. And I have charge 1 operators, I have charge 2 operators, and so on. So this delta min of Q is if I draw some line here, connecting all of the lowest dimension operators at any fixed charge. So this thing is nice because it exists in any CFT. I don't need to talk about tower of operators. And instead of this conjecture, I'm going to rewrite this. And say that a moduli space means that this delta min of Q is just linear in Q. So in the supersymmetric case, with the BPS bound and everything, this is trivially obeyed. We have this tower of operators. But now this condition can also be written down in some generic CFT, even without an R symmetry and no protected operators. Second reason why I like this definition, this delta min of Q, is that this thing has been discussed extensively in the large charge literature. So in the large charge program, which the modern version started off with this guy, with this paper. So what these guys did is write down a very nice algorithm for computing this thing, at least in the limit of Rogen of Q. They found very interesting behavior. So for a generic CFT with no moduli space, this delta min of Q behaves as Q to the D over D minus 1, where D is just space-time dimension, plus corrections that are smaller in Q at large Q. So this is at large Q. This is very different from the case with the moduli space. The way you get this, you don't even need some heavy machinery. It's basically dimensional analysis. There's a very nice argument that tells you that the only result for delta min of Q has to be this Q to the D over D minus 1. And the only known counterexample is either a free theory or these BPS operators I mentioned, where delta min of Q is exactly linear in Q with some known coefficient here.
Everything else has to be superfluid.
There's no known counterexample. It doesn't have to be superfluid, so this is not superfluid yet. So even a free fermion, it's not a superfluid, but it still has this behavior. So this behavior is more robust than calling it a superfluid.
I see.
But there's no
I see. You just need the energy density to be uniform.
Yes, the energy, that's right. The energy density not to blow up or go to 0, and then you have to end up here. But this is a counterexample because the energy density thing blows up and then when you have a moduli sort of free theory. Yes, that's right. Good. So now the question is, where do we fall? So in our case, all we're putting in is if we have a moduli space, what happens? This would still be very interesting because we don't have any protected operators and still we have some exact results. And we want to find out what exactly the correct condition is on the right hand side here.
Sorry, but in your 3D n equals 1, there is
Yeah.
no q.
No, I'm going to write down a different theory. We have other theories with symmetries. That was just the simplest example. But for example, you could look at the very simple example.
I just mean that statement cannot cover all possible.
That's right. That's right. I'm still assuming there's some U1 symmetry that's broken up the moduli space. Otherwise, I don't know what to say. I don't have some nice statement yet. Okay, let me now write down an example. This example is a 3D n equals 1 theories with also some U1 symmetry that's spontaneously broken. And now I want to try to prove some version of this statement. So what I'm going to do is I'm going to use methods from the large charge expansion, specifically the moduli space CFT, to try to see how delta min of Q behaves with Q. So I don't know what to call this method. Let's call it the moduli space EFT method. So it's a very simple calculation. There's 3 steps. Step number 1 is I just write down the moduli space EFT. So I assume there's some operator phi that gets a vev, which is very large in whatever units. And I write down the EFT around this very large vev. This sets some scale, and so I can integrate out a bunch of operators and be left over with some massless particles that I have some control over. We're basically going to see that large vev means large charge in some sense that I'll make more precise. And so doing this moduli space effective action is another way of taking the large charge limit. The next step is I'm going to put this moduli space EFT on the cylinder. So put EFT on the cylinder and S2 times R. And I'm going to find the ground state energy at a fixed charge, at least in the limit of large charge. The reason I'm doing this is because step 3 is now just to do the state operator correspondence, which maps the ground state energy at fixed charge to the minimum dimension at fixed charge. So these two are just going to be equal, and so if I find this, then I'm done. Okay, so let's go through this. Let's go through this argument for some general 3D CFT. The hard part is step 1, and then the other 2 have been basically done for me. So step 1 is just write down the moduli space CFT. So this is done in 2 steps. First, I write down what I think the massless particles should be on the moduli space, and these are completely fixed by spontaneously broken symmetries. So I have a spontaneously broken symmetry, which is my conformal symmetry. When I give a vev to some operator, this phi, since this has some dimension, once I give it a vev, I have some spontaneously broken dilatations at the very least. And so I get Goldstone bosons. And you only get one Goldstone boson when you do this. You get something called a dilaton. So we expect at least one massless scalar of a dilaton. And I'm also assuming some U1 symmetry spontaneously broken. And so I get a Goldstone boson. So I'm a Goldstone boson phi for the spontaneously broken U1 symmetry. So now I have my massless particles. What I need to do is write down all of the possible terms that can appear in the Lagrangian that preserve the symmetries and are only functions of these 2 fields. What we're going to do is write down the Lagrangian in expansion and derivatives. So I have a 2 derivative term, 4 derivative term, so on. And this expansion is the same as expanding in 1 over the vev and 1 over v. Let's write down the most general 2 derivative term out of this dilaton and Goldstone boson that is compatible with the Weyl invariance with my U1 symmetry.
Your conventions are that the dilaton has vev 0 or it has vev v.
It will have vev v.
But then you should have some odd derivative terms in general.
Oh no, okay, let's assume some charge integration. You can also do the general, the odd derivative terms. I'm assuming some charge integration for simplicity. So the 2 derivative terms are just going to be the kinetic terms. On some general manifold, we have a conformally coupled scalar theory for the dilettante, so the conformally coupled scalar. Some standard kinetic term on some weird manifold, plus a coupling between the dilettante and the Goldstone boson, which serves as a kinetic term for the Goldstone boson. So this is some coefficient I don't know. This is a Wilson coefficient. Because this is just an effective field theory, I can't fix this from first principles. But this entire term is just a dilettante times d pi, which this is the only one that can take. And this is the entire two derivative term in Lagrangian. So the only unknown is this one coefficient here. And in principle, you can keep going, you can write down four derivative terms. There's many more terms for derivatives, many more Wilson coefficients, and it just gets worse and worse. But in principle, this is some algorithmic thing you can sit down and do. Okay, so that was step one. Now let's do step two. So imagine putting the entire AFT on the cylinder and looking for a ground state energy, at least in the limit of large V or large Q. So the large charge guys wrote down a guess for what the form would be of the fields that gives you the ground state energy. So this is called the helical solution. It's very intuitive. So just using Nettel's theorem, since the symmetry in the EFT just acts as translating the Goldstone boson, the charge from the CFT is given by pi squared times d0 pi plus some corrections at higher orders. And so to get finite charge, what I need to do is to set phi to be constant and set this Goldstone boson to depend linearly on time. This is some constant times time. So this gives me some finite charge. And now we can see that the limit of large charge, if I want Q to be large, then I can take this V to be large. And so the limit of large VEV, which is what we've been doing all along in this modular space effective action, also just means taking large Q. So this is why I'm calling this some large charge limit, even though in practice it was just a large VEV limit. So the large charge guys have some conjecture which tells me that this solution, if I plug that into the energy, that will give me a ground state energy at fixed Q. This has been proven in some cases, but in general, it's still a conjecture that this is the true ground state. It is some state. There might be lower states, but in all the examples that they've checked, this is the true ground state at fixed Q. So let's find what this is. At two derivatives, it isn't hard. This was by Lagrangian, then you can imagine what the Hamiltonian looks like. There's just some signs that maybe switch, but very schematically, the Lagrangian looks like phi squared, so this should look like V squared, which means that since Q is also V squared times U, the ground state energy is just of order Q. So at the two derivative level, what we found that this ground state energy in the cylinder is equal to some number times Q, at least at two derivatives. Good, and we're almost done. Now we do step three, which is to just map everything back that space. So by a state operator correspondence, what we found is that this decrement of Q, at least at two derivatives, is alpha times Q. Okay, so this is very close to what we wanted. Of course, we have corrections that we haven't taken care of. So one is higher derivative corrections. So it's 4 derivative, 6 derivative terms that I haven't included yet. There's also quantum corrections that I have to take care of because I'm expanding around some weird vacuum. So what do the corrections look like? So let's start with higher derivative terms. Let's do the 4 derivative terms. So a 4 derivative term has to have 4 derivatives, but dimension analysis, because we're in 3 dimensions, fixes the coefficient here to be 1 over phi squared. So the only way to get the correct dimensions is if I use the dilettante itself with this power. And now we can see the contribution to the ground state energy. So what this looks like once I plug in the VEV is 1 over v squared, because phi is just v, which will give me 1 over q. So a 4 derivative term gives me a 1 over q correction, and then higher derivatives will give me higher and higher powers of 1 over q. So at the very least, we have something like a 1 over q at 4 derivatives, and then over cubed. So
why can you not write the fractional derivative that people usually write in the superfluid only theory? D
Can you
pi
repeat that?
cube, I guess.
I missed it at the beginning.
Why can you not write the fractional derivative that people usually write in the superfluid only theory,
Same
d
question.
pi to the d, I guess, or d plus 1?
So in the superfluid, the way the fractional derivative comes from is from a term which is L d to the 0. It's a zero derivative term in that superfluid. The derivatives come in, it's basically the cosmological constant in that theory. There's no cosmological constant in our theory. The reason is that what this would have looked like, just from dimension analysis, is phi to the power 6. And this is a potential, and this is a moduli space. So the reason we have no d to the 0 term is the fact that we have a moduli space, and this would have been the analog of this fractional derivative. In general, the reason you got the fractional derivative in the first place there was because you're expanding around some weird vacuum, whereas in this moduli space, we don't expect some non-analyticities to show up. When you write the moduli space effective action in general for supersymmetric theories, you don't expect fractional derivatives or anything non-analytic to show up. It's this weird fact about the superfluid that gives you these. But at the basic level, all I did was just use the symmetries in the massless fields, and I get nice simple powers of derivatives of the field phi. I'm trying to say that even the superfluid, it's not that I wrote down some expansion and I told you what powers of derivatives you end up with. Even in the superfluid, it's actually a zero derivative term that gives you this weird fractional derivative. Okay, so quantum corrections. So without proof, I'm just going to tell you that basically your H bar in this theory is 1 over Q. So that in the 1 over Q expansion, quantum corrections are going to show up with powers of 1 over Q. For example, so with Q, the next term is going to be order 1. Then you're going to get a 1 over Q at 2 loops, and then at 3 loops, 1 over Q squared, and so on. Good. So now we can amend our initial hypothesis. We have almost proved it. So it's true that at leading order at large Q, delta min of Q is inner in Q, but the correct answer is that there's also corrections. So the linear term is only true at large enough charge, or in the asymptotic limit.
Right, now you don't want to assume the fact that there's a chiral ring.
That's right. So this is now a general statement about moduli spaces with any spontaneously broken U1 symmetry. And this is almost a proof. The only thing that's really left over is to show that these coefficients are non-zero. So in general,
Sometimes they're 0, because it could be an.
that's right. In fact, all of the examples I've shown you up to now, these are 0. So what I did up to now is just assume there's a moduli space, write down the effective action, and get this result. But it could be that the only way to get a moduli space is if there's some combination in the effective action terms, which make all of these things vanish. So I need at least one example where I can actually compute them and show that they're non-zero. Let's see if I have. I'm going to skip the example. I'm just going to tell you that if you sit down and do examples, it's easy to show at least that this term is non-zero generically for 3D n equals 1 theories. And we expect all of the rest of the terms to also be non-zero from genericity. So there are examples where at least this first correction can be shown to be non-zero. So instead of a hypothesis, let me say, this is now a result. This is the type of result we were looking for, some universal statement for CFTs with moduli spaces, at least if we assume a U1 symmetry, which is that delta min of Q is linear in Q asymptotically with some corrections that you can compute algorithmically.
Wait, sorry, I still don't quite understand the answer to this question. If you just say CFT with a moduli space with U1, why do you get to use supersymmetry to restrict the effect?
I haven't used supersymmetry.
But then why don't you end up with fractional powers of Q? Like
That's not supersymmetry, that's saying analyticity. Oh, sorry, fractional powers of Q. The powers of Q did not have to be integer. This is just in 3 dimensions. So for example, in 4 dimensions.
sorry,
You've done the
in
same
3
thing.
dimensions in the superfluid phase, they're not integer powers.
Let me say it differently. So in the EFT, you always have integer powers of the derivatives. That's not necessarily integer powers of Q. But I will also always have integer power derivatives because I'm expanding around some vacuum which I expect not to be singular. The way I
I
actually
thought
do
you were
this,
expanding, you're not expanding around the origin, so you could put non-integer powers of the derivatives, right? That was why I was asking what.
no,
what
even in the superfluid, so you write something like this. I understand the question.
Yeah.
Yes. So in the superfluid, what happens is, the way I didn't go over how I write down all these terms, how they're constrained by one invariance. What you actually do is you find a new metric, which is the dilettante decimal power, I don't remember, something like this, times the old metric. And now all you have to do is write down all the possible different variant terms in terms of this metric G hat.
Yes,
And now forget about the fractional derivatives or anything. I just have to write down, I have this Ricci scalar and I have more squared terms and so on. Plus the cosmological constant.
yes,
The fractional derivatives in the superfluid come from this term. So if I write down the cosmological constant and then rewrite it in terms of my boson boson phi, you get a fractional derivative. It's not that I'm inputting, I'm not telling you originally that I include fractional derivatives in my effective action. It sort of comes out from this term, the cosmological constant, and probably the other terms as well. So I'm doing exactly the same analysis I would have done for the superfluid. It's just that when there's a modular space, you don't get fractional powers of derivatives.
what prevents you from writing Ricci scalar to a funny power?
When you expand it around whatever web you're looking at, it's going to be expanded in terms of integer powers. This is your question about if you're working around the origin or not, around B.
Yeah, but if we're not
That's
working
right, then you would,
around the origin, then Ricci scalar to a funny power times
whatever, yeah.
seems like it would be okay.
Yeah, I don't have a good answer to that right now.
Wait.
What, even when you just read down the modular space effective action,
Maybe your moduli space effective action also has to work in flat space.
then what?
Maybe it
I mean,
also,
it does, but then what? Why is that enough?
some restriction on the coefficients, no, I'm not sure, we can talk about it more.
This is not a model, this is just an EFT thing, right? It's what type of powers of derivatives I would allow. I mean, this would just remove all the power of EFT. If I can write down any power of R, then there's no expansion that I can really write down. It's any fractional power. But yeah, I don't remember what the argument is for why I can't include any fractional power.
Well, I guess you kind of assume that there's no like degrees of freedom
Beyond
the
what I know.
EFT, so it has to be local.
It's locality, okay. It's locality.
Yeah, it's
that's
kind of
right.
an assumption, right? That there's no other like degrees of freedom in the effective filter.
No, but I guess Luca, maybe I'm a bit muddled, but I mean, in the large charge story, one does write the, derivative of the Goldstone boson absolute value. Right?
But I guess the key thing is that the expansion of fluctuations has to be local, or whatever you do.
Yeah. Right, so I was just trying to understand in this context. Is phi the fluctuation?
No.
Phi is not the fluctuation. Since phi is not the fluctuation, then it sounds more like I could write something. If I follow the logic that happened in the superfluid case, I could write something that was non-analytic.
But the logic is the same here. You don't actually do an expansion derivatives. You do an expansion in the metric, in derivatives of the metric. So the question is why here you only got integer powers. If you assume this, then you get the superfluid and you get my result with only integer powers. But even the superfluid, you assume integer powers of derivatives of the metric.
Oh, okay, maybe it's, so maybe it's the fact that the metric is actually the fluctuation already, like that's gonna go onto the Minkowski part, just the conformal factor is gonna get at that. Okay, yeah, maybe that's enough.
Maybe I have a related question, or I might also just be confused. So in the superfluid case, people also write this G hat, and then instead of phi squared, it's square root d pi or something times G. Why can't I also do that in your case and just say, oh, I can build many invariants, you know, I can build many conformal invariants that would involve
Yeah,
either
so you can
combination
also
of
write
these
something like
times.
behind, whatever this means.
Yeah, as another g hat tilde, and then say, oh, that's another conformal invariant building block.
I include this as well. I mean, okay, let me
Uh-huh.
say. What you actually do in the superfluid is something like this. 1/4. Yeah, the reason is you're doing this because you're using Weyl transformations, right? You're saying a Weyl transformation can basically let me get rid of the dilaton because the Weyl transformation takes phi to omega to the delta phi, and it takes g to something like omega minus 2g. So what you're saying is, oh, I'm using a dilatation to set this to 1, and that sets this to be phi squared. So it's not that I'm not looking for conformal invariance. I'm using a notation to get rid of phi, and then I can just use the metric and the boson to write down all of my possible terms. So what you did in the superfluid is do the same trick, but you don't have a dilaton, you have this boson instead, and then you do the same trick to set d pi, square root of d pi times g, the square root of d pi times g to be 1. But it's not that I'm writing down all of the things that are conformally invariant. I'm using the notations to set this to be trivial at the expense of changing what my metric is. And now I can use this metric plus the boson to write down all the possible terms. So there's also terms like, you know, r mu nu, d mu pi here that I need to add, but the dilaton is gone.
But why is there not the dominant superfluid term then? Why is there not modulus of, where is
That wouldn't be Weyl invariant. So just
Why not?
I thought your construction was such that g hat and d pi were independent Weyl invariants.
You said the CC was 0 maybe for some reason, or what was that?
because the only possible CC I could have written down is this. You can't actually write down this thing. And for this to be Weyl invariant when I also have a dilaton in my theory. This is the claim. But this thing on its own is not Weyl invariant, and this construction shows it. I don't know how to show it. First principles, this is not Weyl invariant now.
Okay.
But so the claim is that once you have also the dilaton, it's not Weyl invariant.
But that seems important, right? Because that would have given you the q to the deep
Yes,
over
that's the
d
difference
minus 1.
between that's right. You're getting
Yeah.
this as opposed to this.
Right.
Yes. Okay, let me really quickly say some things about what we expect these coefficients to look like. So there's a new program called the holographic swamp path program. What this basically does is it merges the Spontan program, which tries to find constraints on EFTs that can be consistently coupled to gravity. So it's something like constraining effective field theories using gravity. As opposed to just the usual bootstrap program, the CFT bootstrap program, which constrains CFTs using crossing symmetry. And the way to connect this is using ADS CFT. So by taking these constraints that people find in the Spontan program, putting them on ADS and mapping it using holography to the boundary, you get some constraint which should in principle apply to CFTs. So this idea has been around for a while, and one of the things that people came up with was trying to map something called the weak gravity conjecture. From the gravity side to the CFT side. So what this says is that if you have an effective field theory that can be consistently coupled to gravity, there has to exist some particle whose mass is smaller than its charge, this is some U1 symmetry. In some units that I haven't told you about. So there's different ways of mapping it to the CFT side because there's different ways of putting this conjecture on ABS. But one idea that Wani and Pamti came up with is if you wave your hands enough, then this statement maps here to the statement that the delta min of Q function that we looked at before is convex. More specifically, there is some charge, so let's say Q naught, such that delta min is convex in units of Q naught for Q naught, which is of order 1.
Not just for asymptotically large charges?
No, because that would almost be trivially obeyed, because I told you that the large charge is only two behaviors that people knew about before, which is this.
But these are conjectural also, these are the only two.
That's right, but I mean, then it would be equivalent to that conjecture and it would be interesting, this thing. To make this interesting, what they did is that they said that this has to start at charges which are order 1 and not at asymptotically large charges. This, the statement is false. So this, we found a counterexample to. But again, we only found a counterexample to the fact that convexity has to start at order 1. So still asymptotically, it could have been true. And the reason this is interesting is because now we have a new phase at large charge, a new type of behavior, where this term is convex, but it's exactly modularly convex. It obeys convexity with an equality sign. So convexity is actually determined by the sign of this term. So if we call this term beta, for this function to be convex, we need beta to be negative or non-positive.
Sure, is beta the term that's universally computable?
Yes, so that's the Casimir energy. This is going to be a one-loop correction. That's right. So it is computable. Universally is a misnomer because it's universal if you only have one Goldstone boson and one dilaton. But in general, you're going to have a bunch of fields, and so it's not some fixed number, but you can compute it in any example you want. And in all the examples we looked at, this thing is non-positive, and we could prove that it's not positive in some range of theories, but not in full generality. So there is some idea that because this is a Casimir energy, it needs to be negative, but we don't have a proof yet. You can also try to constrain some of the other terms. You can try to constrain this term. We're trying to find an upper bound on this term as well. But yeah, that's a little harder than trying to show that this thing is negative. So let me summarize that. The summary is just the statement here. What we've done is we found some universal rule for constraining CFTs with moduli spaces, assuming there's some U1 symmetry that also is broken on the moduli space. It's just this simple behavior of the delta min of Q. We also looked at the generic case, where we're not assuming some U1 symmetry. That's a bit harder. What happens there is that you have some 2-point function, let's say something like this, and I give O of F. And now I'm going to expand this thing into different limits. So one limit is if the Bev is very large, or let's say the distance times the Bev is very small. Since distances are small here, I can just do the OPE. So this is one way to write down this 2-point function where I'm summing over all the operators. Or when distances are very large, I again use my moduli space effective action and I get some decoupler term plus a dilaton exchange of these two plus corrections. And now you can look at the two sides of this equation, and what it's telling you is that the effective action we wrote down before is still somehow related to these OPE coefficients and these dimensions, but this equation is much harder to get real information from, as opposed to this simple limit where we also assume there's U1 symmetry. So you can also do the generic case, it's just hard to get a simple one-line answer for the construct theory to have a moduli space. Okay, thank you.
Questions? I have another question. So let me assume that the only light particle on the moduli space is the dilaton. So quantizing that, wouldn't I also get integer spaced operators just from, or at least approximately integer?
You would, but you'd
But
be
they're,
wrong.
maybe they're.
So the reason is that you can't actually use the EFT to do that. So you're saying just use the dilaton and we'll write down its potential. So what happens is if I just write down something like this is what you want to write down. So this is a solution to the equation of motion, and it's just the same thing we wrote, except it's the real part of whatever we wrote. The problem is that the dilaton starts far away from the origin, but at some point it has to hit the origin of the solution. And so you're at zero gravity. So your EFT is not valid for the full range of the solution.
Yeah,
What happens in my example where I also added the Goldstone boson is I have now a two-dimensional theory.
yeah, you can keep it away in the other
Yes,
direction.
so the EFT is always valid when I plug in my solution. But in your solution, it's not always valid.
But you can't make an argument that that is valid for large
We've been
dimensions.
trying. So what you want to do is say something like, oh, but there's some boundary here. So
Yeah.
the EFT is bounded, and then they need to specify all the possible boundary terms. We've been working on that. Even there, it's not clear what is the statement you would want to make, because you want to say, oh, asymptotically, there's not integer space, but some constant space
Yeah.
operators. I think that's true in any CFT, because the CFT spectrum is something like, here there's a few operators, and suddenly here you just get a mess. You're gonna find a bunch of operators
Yeah,
here.
there's nothing special about these.
Yes,
operators.
how do you pick out the operators which are almost integer space? So I'm not even sure what the statement is you would make that is the analog of this without a U1 symmetry. So with this, there's some charge, and you say, oh, the special states are the ones with minimal dimension of fixed charge. Without that, I don't know what the statement is. So you can do what you said. I think we even have some version of this in our paper where you add a boundary and then you say it's integer space up to some 1 over n to some power. But I'm not sure that's a meaningful statement.
So you wouldn't know how to say, like, in this 3D n equals 1 ABC model.
Right.
What's special about the operators in that theory?
Yeah, we don't have a good answer. It's also not clear how to approach it. You can't do like real numerical bootstrap because they have a hard time going to large dimensions, which is where you'd expect this thing to show up. Yes, for the ABC model, I'm really not certain, except for finding some way to make sense of this equation. Exactly, finding some trick to solving this equation. I'm not sure how you would proceed.
Can you do some sort of analytic bootstrap using the fact that the right-hand side, the large X limit has to reduce the leading term on the left-hand side?
We've tried for a long time. We couldn't. I think this is the answer, but we did. Yeah, it's hard. So what you do is take the large, like the infinitely large limit, say, oh, okay, so here's an equation. Clearly, this is obeyed in the free theory. You can write down the free theory. What happens is that the sum here truncates. There's only like 3 terms, and so it's easy to see that you can see that it matches with this side. In the general case, we could not make any progress with this equation, with how this side maps here. The problem is that what dominates is the very large dimension operators. Right? What you have here is so the largest dimension operator dominates, and that's hard to make sense of. But yes, this is the equation you'd like to somehow solve to tell you what a modular space really means. You can do some stupid things. So you can prove with this equation that if one operator gets a VIF, then there has to be an infinite number of that gets a VIF. That you can do pretty easily with this equation. But I don't think we got anything more out of it.
Does your work shed any light on this perhaps conjecture that for interacting theories, the only theory with a moduli space has supersymmetry?
No, that was also part of the motivation. We don't have any, this doesn't have any more. We were hoping that, yeah, somehow you would at least have to prove that fermions
For
have
instance,
to-
that there's a fermion.
Exactly.
Yeah.
That was the easiest part, and even that we couldn't do yet. But I think that would be a starting point. Yeah, prove that there's a fermion in this modular space.
Yeah, I had a similar question too. We had 2 kind of questions at the beginning, talk about the second one. Can you say anything about whether you know if there is a moduli space given CFT?
If you have the CFT data, then you have to at least check that. So that's a necessary condition. yeah, that's it. If there's a U1 symmetry,
If the,
if there's a U1 symmetry, yes.
but I mean, it might not
Otherwise,
be
no, I don't have-
spontaneously broken on your moduli.
Yeah, but like I said, this is it's hard to get examples that are not of this form. So the ABC model I wrote down might be the only example I can think of that does not have a U1 symmetry. And in the moduli space. Okay, maybe you can, if you work hard, maybe you can find another example. But even for theta equals 1 generically, you're gonna have some U1 symmetry.
Any more questions? All right, let's thank Adar again.